Okay, much like question 5, question 6 is about waves as well. This time we have a standing wave in a pipe, in a pipe that has one closed end instead of two closed ends. So we're getting a different shape here. And the first question, apologies, there wasn't a huge amount of space to write in here, but it does say outline how the standing wave is formed. This time it's worth 1 mark. So we're looking for the absolute basics of how the wave becomes stationary. So how that happens is the incident and reflected waves superpose. 6b is asking for you to represent the direction of motion of the molecule at position x. So X and Y represent the equilibrium positions of two air molecules in the pipe. The arrow represents the velocity of the molecule at Y. So we're looking for the equivalent arrow for X. So what we do here, it's very simple. You look at where the wave is in respect to the equilibrium position. I'm just going to redo that. So we can see for all of the blue section, it's in the to the right region. And I'll just show you the equivalent bit. For this bit, below the equilibrium, it's in the to the left bit. So anywhere along this section that I'm drawing in black, the particle is going to go to the right. And then anywhere, I'll do it in green, and probably to about here, where the red line would meet the equilibrium if the pipe was longer. Sorry, I shouldn't have done that. The particle is going to go to the left. So all you simply need to do is look and see where is it in line with. It's in line with a blue part of the wave, a right part of the wave. So the answer is to the right, and we're just looking for an arrow like that. Label a position N that is a node of the standing wave, that's 6C. The node is a position of 0 displacement. Okay, so I'm just going to remove all the color. I'll just put that arrow back on there for later. So a node is a 0 displacement point. So it's here, N, or you could have placed it here, N. Of course, you need to label it to get the mark. It's not enough just to put a dot. If we're trying to calculate the frequency and we've got the speed, we just need the wavelength. We're not given the wavelength, much like a similar previous question, but we're given the length of the pipe. So before I plug in any numbers, I'm just going to write out the formula and rearrange for frequency. Okay, so I know that the speed is 340, which is what is expected in air, and then I need to divide it by the wavelength. I don't know the wavelength, I need to find it. So I'm just going to scroll upwards, and I'm going to label the length of the pipe as 0.3. So we've got, I'll do this in red. So the length of the pipe is 0.3. And what I can do is I can split the wave that I can see into 3 sections, 3 quarters, if you like. I've got a half wave down here, and then I can split this half wave into another half. And then I can see that at the end of the pipe, they've made it fairly simple for us to note that the next bit of the wave goes down to the trough. So that's an additional half of a half. So if I just remove this circle. So what I've got is a quarter, a quarter, and a quarter. Okay, so I've got 3/4 of a wavelength. Okay, so 0.3 meters equals 3/4 of a wavelength. So I can rearrange for wavelengths. Okay, and then plug that in. And if I do, I end up with a frequency of 340 divided by 4 times 0.3 is 1.2, divided by 3 is 0.4. So the wavelength is in fact 0.4, and the frequency comes out as 150 hertz. Good practice to put in the hertz. So for 6E, the loudspeaker is now emitting a sound through the air and into the water. And as it's moving from a different density from air to water, it's going to change speed and therefore change direction. So we will get refraction occurring potentially. So we've got the speed of sound in air. So they've given us the speed of sound in air, which is 340. And they've given us the speed of sound in water, which is 1500. And we're asked to determine the maximum angle at which the sound can enter the water. Now that's actually the critical angle. That's what they're asking for. Okay, so you needed to recognize that. So we're looking for the critical angle. Beyond the critical angle, it's going to totally internally reflect. So that's not possible. So I'm going to go ahead and label these up. So we've got V1, V2. Okay. And then we're looking for the critical angle. If you look in the data booklet, we know that N2, so the second refractive index over the first refractive index, is equal to V2 over V1. Apologies. I've written that wrong. Sorry, I need to, it's V1 over V2. Sorry, I just wrote that incorrectly. V1 over V2. Now, I also know that N2 over N1 equals sine C. So, what we can say is that sine theta C equals V1 over V2, which we do know. So we've got 340 divided by 1500, and so sine theta C, so theta C is the sine to the -1 of that answer, which comes out as 13 degrees. For 6F, it's saying, well, if it doesn't totally internally reflect and it does refract, how is it going to refract? So there's two elements to this. The first one is that we're going from less dense to more dense. So each wave is going to refract, it's going to bend towards the normal. So we're going to get a bending towards the normal like that. And if we do that, sorry, they're not particularly uniform lines, but if we did have uniform lines, you would notice that the distance between them is the same, and it's also greater wavelength than